It is the second part of section 8.5, internal and external measures of cluster validation. Okay, let's begin with the internal measures. The first one is the SSE. It is good for comparing two clusterings or two clusters. The SSE is measured, defined in this way. Now, look at this portion. That is now sum from each cluster. So that portion is the within the cluster of variance. So SSE is the sum of within cluster variances. It can be used to estimate the number of clusters. For example, for this data set, if you perform clustering along with the small number of clusters, for example, start from 1, then the SSE, the total variance will be large because, for example, if you choose one cluster, then the cluster center will be around here, and the variance will be measured from this point to every point, so that the variance will be large. However, if you choose 10 the clusters, then for each cluster, the center will be found, and then variance will be measured separately, and then later on, and they will be summed, so that the total, the variance will be small, as in this figure. So it's going down, and theoretically speaking, it must be going down continuously. Now here, along with this picture, you can decide the number of clusters. That's called knee analysis. This knee shape usually, around there is changing rapidly. Among this region, try to find here the portion which hit from the knee at the ground, so that can be chosen here. So 10 is, for this data set, 10 is the right choice. Okay. Now, here, cohesion and separation. The cluster cohesion is measuring how closely related the objects in a cluster, so that is eventually same as here, the SSE, within cluster sum of squares, so that there's each cluster you are measuring variance and summed. So that is measuring the clusterness between object in each class. Now also, that is called here cluster cohesion. And now cluster separation measures how distinct or well separated a cluster is from other clusters. So that, for example, these are the center of the whole data set, and then mu I is the center of ith cluster, and along with some weight based on the number of points in each cluster, you can measure such a between cluster sum of squares, so that now if it is the number will represent how the clusters are separated. And here WSS and BSS, if you make a sum, then here there is a total sum of squares. TSS is a constant, and no matter how you choose K, it'll be always the same value. So here one example is given, and for that one, you may, okay, for this data set, you may consider this one as a cluster or now two clusters. Either case, now WSS and PSS are different. However, their sum is the same. Okay, here the cohesion and separation are not directly used in most cases. However, the idea of cohesion and separation can be used for so-called silhouette coefficient. Silhouette coefficient combines ideas of both cohesion and separation, but for individual points. Okay, for each point ith point, first we calculate AI, that is average distance of I to all other points in the same cluster, so that within cluster, the average distance is measured to assign AI for the ith point. Now, next we'll try to compute the BI. That is, now for the ith point, we measure average distance to the points in another cluster. So, for example, we have 3 clusters. Then now ith point is here. Then BI start from the average distance for other point over there. Average distance is made, and again here, average distance will be made for that cluster, and among them, here minimum, the smaller one will be chosen for BI. So with that, the values, the silhouette coefficients for the point I is defined in this way. SI is 1 minus AI over BI. And typically, SI is between 0 and 1. Occasionally, it can be smaller than 0. But for good clustering, the value must be between 0 and 1. And the close to 1, the better. Close to 1 means that here, that is small. Once AI is small, which means that, and within cluster, average distance is small. And now BI must be large, which means that it is well separated. So it is the idea is a combination of cohesion and separation. And also, we can calculate the average silhouette width. So for all points, now this score can be averaged. Okay, let's go to here the results. Now, along with the silhouette analysis, we try to select K. And now, for K means clustering. And for the data set, here, once we choose case 2, then now we have 2 clusters like that, and 1 and 2. And here, the silhouette scores are here displayed. For each individual points, the value, this is indicating the magnitude of the value, and is sorted from largest to smallest one for this cluster. And for second cluster, now again, we are measuring the silhouette coefficients, and from largest one to smallest one, and displayed in this way. Exactly the same way, here, when case 3, we can get that one. And for case 4, we have here one. Now there's two. Okay, 2 and 3. Okay, 3 and 4 clusters. And once you choose case 5, then here now these clusters are made and the corresponding silhouette picture, the figure is given in this way. And for now case 6, you have them. Okay. Now what can you do with them? Here in the beginning, for example, for that one, now silhouette scores are lower than average. This vertical line, red vertical line for each figure indicates the average silhouette score. So for that one, this one is way smaller, which means that clustering is bad. And earlier we saw that the bigger, the better. It's a small values, so that for that related cluster, and it's really bad. So once some cluster has a value smaller than average silhouette score, that is not a good one. So this one, and also here, that one is also bad. Now, for this one, your largest one is larger than the average. However, majority of the points are smaller than the average. So it is not really good. So we discard here. And for the case here now, 3. And here, and that one, 5. And case 5, and case 6. And remainders are here and 2 and 4. But here silhouette analysis is ambivalent in deciding between 2 and 4. However, now we will decide this one. The reason is that here, now that is not really completely uniform in the silhouette scores, and then this is more or less uniform, and also the thickness is not really uniform. One is much larger than the other, but over there the thickness is almost the same, which means that each class has more or less the same number of points, so that eventually we decide here case 4. Okay. Okay. When the case 4, all the silhouette subplots are more or less of similar thickness, so that we choose that. Okay. Okay. Now another way of picking K with silhouette analysis is now illustrated in this figure. For that data set, if you try to make a picture for average silhouette coefficient with respect to number of clusters, then you can see here maximum value for right number of the clusters. Okay. So it is another way of selecting K using silhouette analysis. Okay, now we have external measures of cluster validity. Entropy. Entropy is defined in this way. Here, first, the probability Pij is defined in this way. For each cluster J, Pij is the probability that number of cluster J belongs to cluster I. So that is defined in this way. So here, Pij, that is by using external ground truth label, you can decide. And here we combine this Pij in this way. That is called entropy for cluster J. And earlier, okay, let's see here now. In section 5.4.1, we defined entropy. So it is a similar definition. Once this Pij is combined in this way, so try to use only maximum value, then purity is defined. And here overall purity is defined in this way. So that by using this entropy and purity, you can also validate the clustering. However, it requires labels, ground truth information. Okay, finally, we add a comment for cluster validity. That is made a long time ago, 1988. However, today, the claim is yet true. So let's read it. The validation of clustering structures is the most difficult and frustrating part of cluster analysis. Without a strong effort in this direction, cluster analysis will remain a black art accessible only to those true believers who have experience and great courage. As it says, cluster validation is quite complicated and frustrating. And however, to get really good hidden structures, we have to do cluster validation. Okay, that's the end of section. Thank you.